Yeah, there we go. Okay, so what we started talking about Monday, and what we'll talk about today are mass spring damper systems. And I had defined at the end of the lecture these two quantities, omega d, which is the damp natural frequency, and the damp period. And where this gets kind of interesting is that if you're dealing with something, not that, like this, so this is the plot of the period, you can say, oh, look, this distance is tau d, which equals 2 pi over omega d. At T1 and T2, the amplitude is different, and it's a decreasing harmonic. So if I look at the value of so many colors, x1, x2 along this curve, I can create a ratio between the two. So x1 over x2 is equal to CE to the minus zeta omega nt over CE to the minus squig zeta omega t plus tau d. And that is equal to E zeta omega n td. It allows me to also define the log decrement. Which is ln the amplitude at the two positions, and it's zeta omega n tau d, or if you do some pretty basic manipulations, 1 minus zeta squared. 2 pi zeta over zeta, square root of 1 minus zeta squared. These are definitions. And again, as much as possible, you're going to be running through a whole bunch of cookbooks in this course. And these cookbooks are going, for chapter 8, are going to tell you how to solve all of these problems. So as much as possible, try to just make sure it's all in your crib sheet. And as a reminder, it's Wednesday, April 3rd, 16 days to go. I'm just like a burst of sunshine. But don't overcomplicate these problems. Now, to sort of toot my own horn, if you're looking for something that will cover all of the material that I will be talking about today, all of the material on Chapter 8, there is already a summary video, vibration summary, that's available to you. But let's sort of go over everything we've done so far. So again, when you look at Chapters 2 and 5, we basically have been looking at acceleration and velocity, and I don't put it on there. But when it comes to chapters 3A, 6A, and 4 or something, you have kinetics, sum of forces equals mass times acceleration, and in various forms. I'm not writing this out for rigid bodies, but I'm implying that the rigid bodies solutions are still somewhat similar, Ig omega, or Ig alpha, excuse me. Work energy, sum of forces equals mv dv ds, or if you're looking at rigid bodies, sum of moments, Ig omega, and then finally, sum of forces m dv dt. But all of it in Chapter 8 switches over to this form of the equation. What is important, what you have to spend time on, and if I can do this, there we go. There we go. Is writing free body diagrams. And you faced a lot of different free body diagrams. This is the simple one. But the goal of that free body diagram is to write this equation, x double dot plus omega n squared x equals 0. And here I write omega is equal to square root of k over m. Whatever is in front of the x term is omega n squared. And one of the problems in this course is we cover so much so quickly that sometimes that gets lost. You're going to write a free body diagram and you'll see different cases. When you write it in this form, it's not necessarily going to be square root of k over m. It might be square root of 4k over m or something of that nature, and you need to be aware of it. Form of the solutions, those are the ones we kind of use. These two right here, x is equal to a sine omega nt plus b cos omega nt. The other one is just the same thing with a phase lag. So psi just sort of takes care of the cos term here. But to be honest, if I have a choice, I'd probably use the first form. It's just so much easier to do things. I think I have updated all of my summary videos, and I have updated my notes. But we used to use a text called Hibbler, and unfortunately Hibbler used to use a different definition for a number of terms. And so if you see them in the lectures or the summaries, you may come across some confusion, so please be aware of that and tell me so that I can eventually recover those. But in Merriam and Craig, omega n is natural circular frequency. Fn is natural frequency. You typically solve these problems, and I would encourage you, you have available to you a large number of solutions already. You have a large number of problems. Don't just look at my answer. They're all obvious. It's all easy when you do it in lecture. But do it yourself. Once you do it yourself, you'll run into all of the problems. And so just the important points. Here it is, just applying the, well, here's applying all of the boundary conditions, or initial conditions in this case. Our position is given at time equals 0. Velocity is given at time equals 0. And you can solve for a and b. You can do the same thing for x, and you can do it in terms of magnitude. You can sort of do the phase angle. But the important thing, again, is know these definitions. We're not going to tell you that. We're not going to provide that information on the exam. We expect you to know that, and hopefully we remember what everything happens. Where things get a little bit weird, and ignore the spring at the bottom. That was a different problem that I was kind of thinking about at some point. Is if you have a spring mass system, sum of forces equals k delta x plus mg, you end up in all of these equations with a static equation which disappears and your dynamic equation. And in the static equation, that term goes away. And again, I think one of the summary videos, I do it a different way. It's probably not a good idea, but there you go. But I do it so that you can actually solve it with the static terms still in there. But what we end up with, whatever this term is going to be your natural circular frequency, which I should look at. Natural frequency, excuse me. I did this curve a while ago. Same thing. It's just showing you the parallels between the two cases or the two solution formats that you saw, the natural frequency or natural period, tau n, 2 pi over omega n, And just like tau d is 2 pi over omega d. The difference between what we've been doing and what we are doing is that here you'll notice that the amplitude never changes. So the amplitude of the vibration always stays constant. And it continues to infinity at constant. So it's not a realistic solution. It's just useful for a starting point. And remember the other thing too, and that's something I kind of want to make sure you know, is in all of these problems we're assuming very small vibrations. So one of the things that we've done is we've said, hey, sine theta is theta, and then we've been able to make a lot of really quick and easy sort of changes. Damping, you end up with a form of the equation where you have a e lambda t. And we can't use the sines and cosines anymore, which makes things a little bit more difficult. But you can see that you write it this form. Right there. And you end up with zeta, which is equal to c over 2 pi omega n. And substitute it in, calculate, and get a general solution, or roots of an equation that look as omega n 1 omega n minus zeta plus square root zeta squared minus 1 omega n minus zeta minus square root of zeta squared minus 1. In both of these cases, again, you are not necessarily looking at the physical solution. Once you have the solution in the form up here, x double dot, so maybe I should write this. It doesn't matter what this looks like. This I'm going to call it I1 x dot plus I2 x is equal to 0. I2 equals omega n squared. I1 is equal to 2 zeta omega n. And you want to write it in that form and not just depend on your free body diagram. Get the roots, you have a general solution. General equation is written there. So if you choose not to use zeta, don't do that. Okay? But if you choose not to use zeta, and people will eventually ask me on Piazza, how can I do this? I don't want to use zeta. I want to solve it my way, and here you go. That's a solution. It's just writing it out as lambda 1, lambda 2, and you write it in terms of the critical damping coefficient. And the critical damping coefficient is the one that you have critical damping, so the fastest to the low amplitude cases that you're looking at. Solutions look exactly the same. You have overdamped and critically damped. Both of these, you'll notice, do not oscillate. They go straight to 0, or straight towards 0, asymptotically. They never reach 0. Underdamped, on the other hand, does have an oscillatory component and a decrement in the height or the amplitude. All right. I have always liked, I prefer actually Merriam's zeta to the other zetas that we've been using, or in the previous text, because I think it's a lot easier to sort of define things. So once you know what zeta is, you can use zeta there. And I have a comparison with zeta from Hibbeler. Doesn't matter, it's just sort of there for you. But you may be seeing some of the summary videos where I sort of refer to the zeta that's slightly different than what you're used to. Overdamped, zeta greater than 1. Critically damped, zeta equals 1. And underdamped, zeta greater or less than 1. So zeta is a really useful term to sort of determine what your equation is, and this is all you need. So if you know if you write your free body diagrams, write all the terms out, get the equation in that form right there, you've solved the problem. And I had to sort of finish the lecture notes on this because I hadn't talked about it. You can talk about damped natural frequency right there, period of the damped vibration, and also this log decrement. Oh yeah, log decrement. 2 pi over square root of 1 minus zeta squared. 2 pi zeta, sorry. All right, and I will continue that set of notes next time, but let's look at an example. So we are going to look at force vibration, and so the bit that I just skipped that I have written already is the force vibration component of the course. That sort of rounds out the discussion on vibration. But let's look at a problem where we do this sort of thing. I have a damper which has a coefficient of 20 newton seconds per meter. I have a spring constant of 32 newtons per meter and a mass of 8 kilograms. Cart is moved 0.2 meters to the right at t equals 0, so I know x at 0 is 0.2 meters. What is the displacement at t equals 2 seconds? So I've let it go. I'm going to let it vibrate over a very short distance, and then I'm going to solve for it. Again, as much as, well, every time you do these, every time you do these, you have to write them in a certain way. And you have to make sure that the final equation that you get out of this is going to be positive. So I have weight, I have normal, I have the spring constant, I have the viscous damping. I have a particle, so life is easy. And so, there we go. I have done exactly the same thing as I've done before. I've written this in a form, so I have stretched the spring out, and everything is trying to pull back, and so my two forces become negative on my force x equation, and because of that, when I write my equation of motion, I have mx double dot plus cx dot plus kx. So all the terms are there. And that's the final equation. Everything else, I start to go back to that recipe book and I say, okay, what do I need to put in here? So in terms of the expressions I have here, I have k over m. And that will equal 2 rads per second. Again, the decision about how you present or keep your units, and again, well, maybe I keep saying it again, unit calculations are really important to your calculations. If you put units, you're going to be helped a great deal. When you're dealing with rotational motion, you don't have to include the rad because it's dimensionless, and so you could write 1 over seconds. But I find it's very helpful to you to write rads over second and keep that term all the way through. Even when you multiply rad by rad, you get a rad. so it's kind of weird, but there you go. Mm. And I think particularly when dealing with these kinds of problems, making sure that you actually end up with something that is in the correct units, kilograms, seconds, whatever you have, is a kind of a valuable sort of thing to have happen here. So zeta is equal to 0.625. So it's underdamped. So when I know that zeta is equal to 0.625, I look at that table and I immediately see I have two forms of solution, the top and the bottom, both of those similar to the solutions that I got before, where I wrote A sine omega nt plus B cos omega nt, or C sine omega nt plus psi. So I have zeta equals to 0.625. So this is zeta under 1, and it's underdamped. So my damped natural frequency is 1.56 rads per second. And again, I'm not doing anything. Once I've done the free body diagram, I've set up everything to solve for it. After I've set everything up, I'm just using the standard, or the formulas as I've been given. I also know what the form of the equation, so in this case I'm using this form right here. I know what zeta is, I know omega n, I know omega d, I don't know psi, I don't know x, or I know x. X is given to me at time equals 0. And maybe I'll put, which one? Okay, no. At time equals 0, x naught is equal to 0.2 meters. X naught dot is equal to 0, which equals to c sine of psi and minus 1.2. Oh, yeah, maybe I do want to do that. Sorry. X dot equals minus 1.25 c e to the minus 1.25 t sine of 1.56 t plus psi. Ugh. Plus 1.56 c e to the minus 1.25 t cos 1.56 t plus psi. All right. So I have a mess of terms there, but those are just the two derivatives. And I can write, first of all, for the first one, set t equal to 0. I know it's equal to 0.2 meters. And so it's c to the power e to the power 0, 1 sine of psi. So c sine psi equals to something, 0.2 meters. Again, doing the same thing, just putting t equal to 0 and recognizing that x dot, because I'm releasing this from rest, is equal to 0, I can put that in. So I get all that, everything's there, all good. Everything is in radians, of course, because you wouldn't do it in any other form when dealing with these kind of problems. But there it is. And this is a great, relatively straightforward problem for you to practice on. So you should be able to get the same result, I hope. I think I've checked it enough. But at t equals 2 seconds, you end up with x at 2 is equal to minus 0.016 meters. Okay. So it's an interesting problem just for the fact that it adds a little bit of complexity, or not much. There's no complexity in this one. The complexity lies in the solution because you've got to keep track of a whole bunch of sines and cosines. But, you know, once you have the formula down, you can, I think I did it. Oh, I didn't. Maybe I'll do that in sort of the updated version of this. You can just put in the solutions to this and you'll get everything sort of worked out, but that's not for now. Put everything together, solve, or do this one on your own because you need to convince yourself how to use the crib sheet. So this is a great opportunity to create a crib sheet, look at how to use zeta, how to set up the solutions to these problems. And again, you're not doing very much other than the free body diagram. Everything depends on the free body diagram. Oh, this is the one. So let's do a small variation to sort of hammer in a point I kind of think is important here. All right. I have a theta there. Doesn't matter what it is. It won't matter. Again, it's a similar problem in the sense that this is K, C, a weight, some mass at the end, mass of 32. Well, the total mass is 32 kilograms for the system. Surface is smooth. If C equals 0, find omega n, Fn, and tau n. And if C is equal to 220 Newton second meters, find omega d, tau d, and Fd. So if C equals 0, you have a mass spring system. If if C is not equal to 0, it's a positive value, so it's never going to be less than 0. It's going to be a damped problem. And I go through all of this trouble to write this, but I really don't need to. Let's ignore that for a second. T1 is rope. Minus, ooh. Cx minus kx equals mx double dot. And oh, what's the tricky bit here? Oh, tricky bit here, I forgot to add, is that the pulley has a mass and it has a moment of inertia. Okay, so the pulley is 0.3035 kilogram meter squared, and the radius of the pulley is 110 millimeters, which means that when I look at the tension in the cable, it's not the same. So I need to consider that. And so T2 minus T1 times radius of the pulley equals I x double dot divided by R. So I alpha. So I have everything I need. I have x double dot that I need to deal with. I have the component of weight. I also have one case where Cx dot is equal to 0, but okay. And, sorry, I'm going to move things because I'm getting better at this. T2 and T2 mg, and I have T2 minus mg equals minus mx double dot. So it's moving down, and it's going to be moving with an acceleration downward, looking at the system I've defined. Okay, T2, I think that's everything. And yeah, I probably should do this. Mg, T1, Cx dot, Kx. And xy. There we go. Oh no. Okay, everything's there. All right, so I have three equations. I have an equation for the free body diagram of the mass, m. I have a free body diagram for the blue mass. I have a pulley, which also has a mass, by the way, and a moment of inertia. So that's making things more fun. And let me see which one I did first. C equals 0, good. So if I eliminate T1, T2, we can get 2 2m plus 1 over r squared x double dot plus cx dot plus kx is equal to 0. And if I go a little bit further, see x dot, x double dot plus x dot plus kx, I am going to end up with CR squared over 2m r squared plus 1 and kr squared 2m r squared plus 1. Okay, so this is one of the first problems where it's the natural frequency for the system is not square root of k over m. In fact, the natural frequency is this thing right here. And if you solve for it, omega n is equal to kr squared 2m r squared plus 1, and that will equal 3.163 rads per second. Okay, no problem. For the frequency, doesn't matter. So 1, 2, C equals. Doesn't matter which it is because it's always going to be the same. 220 Newton seconds per meter. We have zeta, which is equal to CR squared 2m r squared plus 1, which equals 5.923. And this is very overdamped. Oh, wait. Oh, sorry. Oh, that's not correct. I did part A and part B in the wrong problem. Sorry. Okay. Omega n is 3.35 rads per second. And if you calculate Fn, it's 0.5329 hertz, and tau n is equal to 1.88 seconds. That's the problem with not looking carefully at which note page I'm on. Okay, so I have all of that, and it's all kind of working. And that is true for both cases. But if I look at the second part of this problem, zeta is going to equal 0.4911, and here it's underdamped. If you're wondering which problem I was doing a car impacting against the surface. It's a forensics problem, and it's kind of fun, but I'll see if I can do it today. All right, so I know that I have it's underdamped. I already know what the form of the solution is. It's kind of messy, but okay. It's the same one as we just had. And I end up with omega d which is equal to 1 omega n 1 minus zeta squared, which is 2.9168. Frequency damped is omega d divided by 2 pi. Ooh, I really should know how to write a 6. Rads per second, which equals 2.46 hertz. And tau d is equal to 2.15 seconds. It's not much harder to do these. Once you have the recipe book, once you sort of apply everything, it kind of works out. But the thing that is interesting about this particular problem is that, yes, it is a mass spring damper system, but the omega n of the system is not square root of k over m. You have to solve through, and this is why in all of these problems, you are writing out what the free body diagram is. Getting to this form of the equation, and then solving through. And so that's your omega n squared, and that's your zeta. Nice. I do like Hibbeler better in the sense that the term in front of the x dot always kind of works out really nicely as an indicator, and you don't have to, or sorry, Craig, Merriam and Craig better, because I like this form of the equation and the solution, particularly the fact that I know, once I know what zeta is, what my solution looks like. And I can always solve it that way. But if you are looking for something to do, those two problems are really good. We can start on the one that I started on. I didn't realize I started on. Now, this is a similar kind of problem to the first example, and it's one where you're looking at mass spring damper, but the difference is this is what you would do with a car. So I have a test car that's impacting against the surface. It collides with a rigid body at t equals 0. What that means, of course, is that it compresses, the rigid body does not. Car's response can be simulated by a damped oscillation with c equals to 4,500 Newton second meters and k equals 12,000 Newton meters. Assume the car moves left with v naught equals to 2.2 meters per second, and the spring is unstretched at time equals 0. Find the car's position at 2 times, 0.04 and 0.08 seconds. I'm getting very sloppy here because I don't really need to do very much in this particular problem. I have done enough examples in my head that every time I look at a horizontal mass spring damper system, I know what the form of the equation is going to be. It's mx double dot plus cx dot plus kx. And I'll divide out the mass so that I have the standard form of the equation. Yeah. So I see immediately that I have omega n squared there, and from that I can write omega n equals square root of k over m, substitute in the terms that I have, and that's where that magical 3.623 rads per second came from before. And if I solve through for zeta, that's just going to be c over 2 mass of omega n, and that mass is equal to zeta of 5.923, and it's very much overdamped. So these solutions will vary dependent on the problem that you're dealing with and what kind of situation you're looking at. But here again, what I see right away is that I know it's going to be an A plus B solution, and I already have sort of a table for that. And so if I go back to my table, this is the form I have. Zetas are greater than 1, either A1 E lambda to 1t plus A2 E lambda 2t, or I can expand it out in terms of zeta, which I have just below, and omega n. So out of that, I will end up with lambda 1 is equal to minus 0.27, and lambda 2 minus 34.68. So if I substitute in all of my expressions, I end up with x equal to 0.595 e to the minus, I just want to check, make sure I have this written correctly. Lambda 1. Oh, yeah, I'm just going to leave it as lambda 1. I'm not going to write out lambda 1t minus 0.0595 e to the minus lambda 2t. Oh, I think it's just lambdas here because I've already put them as negatives. Okay, and so I have a decreasing function that is going to start sort of slowly reaching 0 over some time. And it's 0.0595 there. So at time x at time of 0.04 seconds is equal to 0.0455 meters. X at 0.08 is equal to 0.0552 meters. And tell me I did, okay. And delta x is approximately equal to 1/3, 1/9, 0.008 meters. Yeah, it's about 0.09. Okay, and that sort of ends today. Tomorrow I will be talking about force vibration. It will be one of the last major topics in vibration.